to capture any interesting comments for after the talk. Hand over to Timo.
That's great. Thanks a lot. Let me just go to full screen. So you should see a full screen picture now. Yeah, thanks a lot for giving me the opportunity to talk here, and it's quite exciting. So today I want to talk a little bit about the journey we took in learning Rust and why we decided for Rust, and talk a bit about the language, and then in the second half talk in much more detail about our current ECSE supported project about sparse linear algebra in Rust. So, but yeah, let's just get started. So, what's actually the background? Where are we coming from, and what have we done in the past, and what actually did drive us to move towards Rust? So, our own software, classical software that we've been working on for over 10 years now, is the MPP library and later the PCL library, which is a boundary element library for problems in mostly large bounded, unbounded domains, like electrostatic problems, acoustic, electromagnetic problems, frequency domain wave propagation problems, these kind of problems. And formulate those with boundary integral equations, discretized boundary integral equations. And this originally started as a C++ project in 2011 with a very shallow Python API on top, but almost everything was C++. And then over the years, we moved more and more features to Python. People do because it's a nice language. And then at the end, we only left the really computational hard bare metal loops in C++. And then in 2018, we decided for a complete redesign and thought, okay, can we actually get rid of all of the low-level languages, go purely Python? And we actually achieved this by doing OpenCL just-in-time compilation, and we produced OpenCL kernels for CPUs and GPU architectures, and then everything was steered from Python. It was fairly nice, and we really liked the code, and it's very fast on a single workstation.
So, sorry, just to interrupt quickly, yeah. You're not quite showing full screen. We can still see the presenter's view.
Oh, I'm so sorry. On my own window, it's appearing as full screen. But then the problem arose for us. We wanted to start scaling up. We wanted to move to clusters, do complex algorithms like fast micro methods, and move to really, really big problems. So the issue there was really our Python code, because Python is a beautiful language and very nice for kind of large array processing if you use just-in-time tools like NumPy, OpenCL, and so on. So and then we could handle high throughput workloads fairly well. But anything that is a complex algorithm with many Python callbacks started being very difficult. And for the kind of big cluster application we wanted to do, this proved to be a serious bottleneck. And we actually wrote a little paper about this with my PhD student Shrika Lasse and collaborators of mine from George Washington University, Tinglu Wang and Lorena Barbe. And the paper is currently in print, should be out soon. And there we are talking about the issues about designing high-performance software with Python and NumPy. And the kind of one thing, for example, we noticed there, especially for complex algorithms, the more we wanted to get around the kind of latency issues with the Python interpreter and Python callbacks, the more we had to shift into NumPy, and the more low-level our whole code started looking like. And at the end, we were essentially just fighting the Python interpreter the whole time to squeeze performance out. And this is when we realized, actually, after our 10 years journey from going to C++, higher and higher level to very nice high-level Python code, we actually started having to go low level again. So this is kind of where we were a year or two ago. So, and then obviously we thought about, okay, what should we actually do now? I mean, we've done C++ for a few years, and then we moved more and more to Python. Shall we move back now? So, and then we thought about, okay, what are alternatives? And obviously Julia is one option, because people constantly talk Julia, collaborators of mine use Julia. And obviously, it promises close to optimal performance and still looks quite high level, but everything is automatically just in time compiled. But there are also issues. I mean, when we talk to people who use Julia for very high performance applications, and they also talk about how difficult optimization can be. And sometimes they need to look into the intermediate representation from LLVM, need to see what's actually being created by Julia. There are all these kind of issues. And obviously for us, a big problem for us as well was our users are used to Python as a front end. And then using Julia as a backend language, that doesn't sound like a very good and appealing idea. We could have also just said, okay, let's go back to C++. And then, I mean, we all know C++, and it's fine, we could have put this off, but then we would have run back into the exactly same kind of problems that originally made us move from C++ to higher and higher back to Python, namely the usual CMake deployment issues, difficulties of complex projects. And our original CMake, I mean, this was old style CMake, then new style CMake is obviously a little bit better, but still huge issues around dependency management, deployment. Skilling up PhD students was always a problem for us with C++. And also a big argument was very little research novelty for us in doing, for example, just another FMM code in C++. Just so many groups have done this for their own purposes. It just wasn't very appealing in terms of novelty and curiosity-wise. It would have felt a little bit like a step back in a regression. So, but over the time, I mean, I like looking at new programming languages, and I had done some projects with MSc students on Rust. So I knew Rust a tiny little bit, and I've been looking and following the community a little bit over the years. And then I thought, why not? Could this actually work for us? So, and we started looking more, and I started finding out Rust, and yeah, it actually could work for us. But why? First of all, for those people in the audience who don't really know Rust at all. So I mean, Rust is a low-level systems language. It really compiles down to bare bones code, so there's no runtime system or garbage collector required. It's got a very modern package management and deployment system, so very much similar to Node Package Manager or similar things, where you essentially just give a list of dependencies when you compile your code dependencies with the correct versions automatically downloaded and integrated into your project. So even complex projects, they've got very small files, essentially just lists of dependency, and the rest is handled automatically. That's very nice, and a big bonus of Rust. Borrow and lifetime checker. So that's very often mentioned as the first argument, but it wasn't actually even the first argument for us, but it's a very important one. So we come to that later on. These are very much Rust specialties, and they prevent most of memory errors that you can have from other languages. Integration into Python, very simple. That was important for us. Growing scientific ecosystem. I mean, we knew that we would start, if we did move to Rust, we knew that the scientific ecosystem would not yet be fully fledged out, and would not yet be as mature as C++, but we needed something. And we looked and we checked, are there actually the libraries that do fulfill our needs? And most of them did exist, and a little bit that we had to write around this was possible. So there's enough of a scientific ecosystem for us to actually make the jump. And obviously, a huge amount of scientific curiosity, just to have some fun with the new language and producing new, which is always a very important driver for us. So let's just get started. So in the next section, part of the talk, I just want to give a general dive a little bit into Rust, just show off a couple of features and what's kind of unique about Rust and how the language looks like. I'm not going to use actual code demos for that because I switch around too much between talk and slides, but I show lots and lots of pictures of code. And later on, depending on time at the end, I'm going to show some actual current MPI code and run some MPI stuff that we've been developing. So, and yeah, but let's just first get started to show people some Rust. So first of all, obviously the usual Hello World app, important for everyone. And if you can see, if you look top left, and I cannot show in this system, I do not have here mouse pointer to show, sorry for that. But the beautiful thing is there's a management system. So if you look at the top left screenshot, there's the kind of infrastructure management system of Rust is Cargo, and Cargo kind of steers the development. It steers the compilation, build checking, unit testing, and all of this. It's all together in one very nice tool called Cargo. And you just say Cargo new demo, whatever you like to call it, and just creates a new project. And by default, it always creates a Hello World project. And if you run it, so you just go into the directory and say Cargo run, it just prints out Hello World. So what has it done? Okay, apart from doing Hello World in yet another language. So there are two important files that are created by saying cargo new. One is the cargo.toml file. This is a file that, very simple toml file, where you simply list some information about your package and the list of dependencies. Here, obviously, in that package, it's empty, but that's all. And even very, very complex projects, you just need to list your dependencies, and that's all. The rest is handled automatically by Cargo. How does the main file look like? There's a file being generated called main.rs, which is obviously our usual hello world, fn main, printline hello world, so usual stuff. If you want to download Rust, just briefly mention, the easiest way to do it is to simply go to the website rustup.rs, and then they have a little script there that you can just download and execute it, downloads it locally for you. So, and then there's a Rust Up manager that does management of the compilers and all this stuff. So there are two main releases. There's a stable release and there's a nightly release. The nightly release always previews features that are still in active development. The stable release, obviously, for stable Rust. And there's a fairly fast development speed available within Rust, within the compiler toolchain. So yeah. So, but what are now kind of the unique features of Rust? So one feature that people always love to talk about is the borrow checking. What's the borrow checking? Sounds strange. It's not so strange, actually. So references in Rust, they're called borrows. Why are they called borrows? Because data always has a unique owner. So if I create some data on the heap during runtime, let's say a new string or an array or so, there's always a unique variable owning this. But obviously you want to have different functions, different things have access to it. So you borrow access to the data. And borrowing access just means calling references. But the references are very strictly managed in Rust. So first of all, once you create a reference to data, you're not allowed to modify the original data after the borrow has been created. Okay, so only obviously if you create a mutable borrow, so a borrow that allows changes, then you're allowed with that borrow, you're allowed to change it. But there's always only one instance that has access to changing data. So you can have an arbitrary amount of non-mutable borrows. So you can have many, many references to data that just reads from it, or you're allowed to have exactly one mutable borrow, but you cannot have both at the same time. So what does it mean in practice? If you look at the right window, super simple code, let x equals 5.0. So we create a new variable, and then we say let y equals reference to x, and let z equals reference to x. So we have the data x equals the variable x equals 5, and we've created two borrows to it, and we are just printing it out, and everything's fine. But let's now look at the bottom picture, and you can already see some red complaints from Rust Analyzer there. Rust Analyzer is a language server from VS Code. It actually analyzes the code while you type, and immediately shows you the errors. So we're now creating a variable that can actually be modified. We say let mute x equals 5.0. So by default, whenever you create a variable, then it's non-mutable. You have to explicitly specify that the variable is mutable. So let mute x equals 5.0. Now we are creating a non-mutable borrow to that, y equals reference to x. So that's a non-mutable borrow. If I wanted to create a mutable borrow, I would have to say reference at mute x. So I would have had to, into the reference, I would have had to include the mute keyword as well. But now I want to change the original data back. I want to say x equals 2.0. I want to modify the original data. It doesn't allow me to do this because afterwards we are going to access the reference again, and it doesn't allow me to access change data while I still want to access references. So this is a very, very strict system to handling data and allowing changes to data, which proves especially good in multi-threaded environments. So the kind of usual errors that you have multiple threads accessing the same data and creating data races and so on, the language just bans it. It's just forbidden. So there are obviously some restrictions to that, and some design patterns of algorithms in Rust, they need to be done slightly differently than in some other languages. So Rust very much favors a data-oriented design, data-oriented programming paradigm, which means the data is in the center, and then you ask yourself actually who currently owns the data and who do I give access to the data. And you want to design algorithms in such a way that you never have multiple ownership for data. So that's one very important aspect of Rust. The second one that people love to talk about is this kind of thing with explicit lifetimes. So that's also quite different from other languages. So, and I would have loved to have it quite a few times in C++ when I did my usual memory errors in the past of having references that are accessing objects which didn't exist anymore, which happened to me a lot of times over my lifetime. So it cannot happen here. So Rust has an explicit notion of lifetimes of objects. So lifetimes of variables, okay? And lifetime checking.
Sorry to interrupt you. Could you just hit the hide on your screen so we can see the bottom of that slide?
I cannot. The slide is in full screen. How much can you not see?
It's just a little bit of code at the bottom. I think it's fine to continue if you can't see how to change it quickly.
Okay.
Thank you.
I'm sorry for that. It's a standard Mac here with Keynote and full screen. So I would not know how to change that around. So lifetime checkings happens at compile time. So, and most of the time the compiler can figure out how lifetimes are, what the lifetimes of objects are and how lifetimes are to be handled. Sometimes it cannot figure it out. And then whenever the compiler cannot figure it out on its own, it actually forces you to tell it. Not like C++ that it lets you do your stuff and lets you run into undefined situation if you're not careful. It actually forces you to be unique about the lifetimes and to be non-ambiguous about this. And if it needs help to do this, then you have to provide it. So, and one other important thing about this lifetime checking, it actually happens on function signatures, not through code analysis, because lifetime checking itself, I think it's actually an NP hard problem. Rust simplifies this. It simply checks function signatures. So what does it mean? So here's a very simple function. I've called it what's my lifetime. It's actually adapted from an example in the Rust from the Rust handbook. So, and we've got two lifetimes here with this it's just quotation A and quotation B, A and B in quotation marks. So lifetimes are actually like generic template parameters. So if you know C++ here, it looks a little bit like template parameters. Lifetimes are kind of like generic parameters. And the function takes two variables. S1 is a string with some lifetime A, and S2 is a string with some lifetime B. I actually called it underscore S2 because I don't access S2 directly in the function, and otherwise Rust Analyzer would have warned me that there's a parameter to the function which is not being accessed. And out comes out of the function just a string with the lifetime of A. Okay. So in C++, you would not be able to model, or in many other languages, you would not be able to model properly what kind of reference is now coming out in terms of lifetime. So you could give it S1, you could give it S2, you could return back something that depends on S1 or on S2, but the lifetime of what's coming out is where you have to be careful as programmer. Rust forces you to tell it, and here I'm doing the very simple thing. I'm just returning S1. So and here, meaning the output has just lifetime S1. So what does it mean in terms of the code? If you look at the bottom left window, I hope you can see everything of that. So here we've got a main function. I'm defining a string S1. And now I'm defining a new code context in the curly braces, and I'm defining here the string S2 within the code block. And obviously at the end of the curly braces, the variable s2 is going to disappear. So it's going to go out of scope. And then I've got a variable out here. I've declared it in the outer scope, but I'm only filling up in the inner scope. Okay. So, and I'm saying here a string equals string word to string, and then I'm saying out equals what's my lifetime, and I give it s1 and s2. S1 exists in the outer scope, and I assign to the outer scope. Everything is fine, just prints it out. If I switch it around, if I have here S2 now, if I handle over S2 in the inner scope to the variable, and I want to pass it on to the out, which is in the outer scope, then the compiler refuses to compile it. And it refuses to compile it because the lifetimes are not going to be correct for that. Okay, the lifetime of S2 is actually too short. It only lives in the inner scope. So that's the explicit lifetime checking. For certain, you might say for certain simple situations, also C++ compilers sometimes say, okay, if I hand back for a reference from a function, certain simple situations, also C++ and other language compilers can detect it if it won't exist anymore soon. But Rust is stringent in the sense it gives you a strict system to always detect these issues, no matter how complex the situation. And there's a notion in Rust of actually, with this lifetime system and this borrow checker system, of actually, sometimes people say in forum, fighting the borrow checker or fighting with the lifetimes. So that's especially when people are new at Rust, and I've been fighting with this as well. But the kind of mantra is always, if you have to, and I had to learn this myself explicitly, if you start fighting the borrow checker, if you start fighting lifetimes, then usually it's not that you're right and the code is wrong, but it's usually that your design is pretty bad and you should maybe rethink your design. Because the kind of restrictions that Rust has, they're essentially enforcing good programming paradigm in terms of unique ownership, proper lifetime management, something that we should always do, but often I've never thought about in the past. The compiler just checks for you. And if you have to fight it, it usually means for me, after a few minutes of fighting it, I'm getting angry, and then I think about my design, and then I notice my design was probably not the best one. And then I just refactor slightly, and suddenly everything works nicely. There are lots of other goodies within Rust. Enum parameters can contain data, which is very nice. For example, we have in some of our codes, we have such a kernel type for different PD problems. Helmholtz problems, modified Helmholtz problems have a wave number, while I just says as the enum type for Helmholtz just takes a complex 64 as a wave number, as additional parameter as part of the enum. So you can do lots and lots of cool stuff with this. For example, just by default, there's an option enum in Rust, which is used in usually instead of a null pointer, so just so that you can model a none or null result. And this has two possible states, namely sum of t, so sum of some data type, it's a generic type t, or none. And a lot of functions have this, that if nothing is to return, it gives you a none option. There's something to return, it gives you a sum of t option. Error handling works very similarly. It's just, again, just an enum. You can return for a function. If you want to do error checking, you can return a result enum, which is either OK of something with the actual result, or error with an error data type. And that actually, it looks super simple, but allows you to do very, very powerful things in terms of errors, which are in a lot of ways, much easier, nicer than to just throw an exception than you do in other languages. In terms of macros, declarative macros exist in Rust, but they're not just string substitutions, but they have semantic context. So you can declare actual types in declarative macros. A compiler can deal with them much better because they're much more than string substitution. And you have so-called pop macros, where you can become as wide as you like, because with those you can actually modify the actual abstract syntax tree that's created. So Rust uses LLVM compiler, and you can do some very deep manipulations in the syntax tree. Other nice things which are beautiful, also handled through Cargo documentation generation. You write your documentation of the code directly inside the code file using Markdown. Rust uses Markdown to write documentation, and then you can write long Markdown, actually including LaTeX formulas, whatever you like, inside the documentation, and then Cargo can handle this. It's really, really nice. So, unsafe Rust. quite important sometimes, for example, when you need to deal with raw pointers or do other things where you have to get around this unique ownership system, then there's something in Rust which is called an unsafe mode, which actually takes back a certain checks. It doesn't take back all checks that it does, but just certain types of them. For example, dereferencing of pointers is always an unsafe operation, and you always need this if you need to work, for example, with C code where you pass data right pointers, or if you have low-level hardware drivers, this kind of stuff, that's unsafe. And unsafe doesn't mean it's bad code. So sometimes in forum you read, oh, it's unsafe, must be bad code. Unsafe simply means that this is part of the code where the compiler cannot guarantee safety, but the programmer guarantees you the safety. And then you just have to, like in other languages, you have to believe the developer. So I have here on the right a very simple use case. Namely, you have an array. You want to split this up into 2 sub-arrays, which you can access independently. You need this multi-threading. If you have one thread running on first half of the array, second thread on second half of the array, you know they are mutually exclusive. One thread is not going to access the other one, but just by default, Rust would only allow you to create one mutable reference. So you have this, you get around this with an unsafe construct to create 2 pointers to the unsafe path. And you might say, no, oh, wow, whenever I just want to have 2 accesses into an array, do I have to do all of this? Obviously, for all of these standard situations, the Rust standard library has function already, which do this for you. So the right kind of code is just illustration. You don't actually have to write this. There's standard function for this kind of stuff, like splitting up an array into 2 sub-arrays and so on. So yeah, for very important for high performance development, SIMD and fast array accesses. So I often get the question from people who ask me about Rust. They've heard that Rust by default does bound checking of arrays, and so isn't it slow? Rust, yes, it does bound checking of arrays by default, and no, it's not slow. Rust, in almost all cases, together with the help of LLVM, is actually very, very good at removing bound check for release compilation. So, and if you look at the LLVM code, in a lot of cases, Rust simply can figure out that a bound check is actually not needed inside a for loop or inside an iterator, because the bounds of the for loop are related to the length of the arrays, and then it just figures out the rest. So it just removes the bound check. In very few cases, very rare cases where it's not able to do this, there actually arrays have unsafe accessor functions, which you can call in an unsafe block to actually say, I guarantee my access. And Rust, even in complex situation, then can automatically remove bounds and does SIMD optimization. Here's, for example, a very simple function. I'm not going into details of this, but it's just you've got one target point, XYZ point, and many, many source points. And it actually computes the norm of the difference between the target points and all the source points. And here I wanted to check, it's part of library routines we need, whether that this is actually done in a without bounds checking and SIMD accelerated without factorization. And actually it's done. So it's very, very nice. One can inspect the code. I'm not going into detailed picture here, but if you look at the LLVM intermediate representation and know this a little bit, you see here this instruction f sub 4 times double and so on. So it uses nice on my Threadripper 256-bit vector registers. So it's all good and all fine without any kind of work. Rust actually does know explicit SIMD instruction for various platforms. And there's also in the nightly build, there are platform-independent SIMD abstractions available. They're not yet in stable. They're still in nightly. I don't know what the development status is when they're going into stable, but work takes place on platform-independent SIMD instructions. So yeah, traits and generics, the last topic I'm going to talk about before I'm getting a little bit a deep dive into our actual current software that we're working on. So Rust, obviously it does support generic types, and properties of generics, they're actually specified through traits, and they're very similar to C++20 concepts, just that in C++20 concepts, they're optional. I think they're optional, and Rust generics traits, they're not an optional feature. They're core bound together with generics. So generics always come together with some traits. So whatever you want to do on a generic, you have to specify what you can do on a generic. You always have to specify it with the trait describing what kind of properties it has. So, and everything that is done in terms of polymorphism in Rust is essentially working through these traits. And by default, you always have compile time polymorphism, but you can actually create so-called trait objects, which are like abstract base objects in C++. So, and structs itself in Rust, so they do not support inheritance, but you can actually have inheritance on the level of traits. So you can specify, you have a collection of traits, and then you can specify traits which actually combine all the collection of previous traits. So yeah, so now to our actual software. What are we actually working on in Rust? We have a couple of projects. We are working on a large integral equation library, which we are planning to run on ARCHER2, target ARCHER2. It's part of an Excalibur project. But I'm not going to talk about that today. Today I'm going to talk about RLST, which is the Rust Linear Solver Toolbox, which is supported by an ECSE grant from ARCHER2, which we were really, really happy about to get. And because it's kind of our first foray into Rust, and we're just trying it out, and is this fundable? And we were really, really positively surprised that the ARCHER2 team decided to support us. So, and it's the development of a linear algebra toolbox for PD discretization problems. And it's actually not the first linear algebra library. There's two very established ones, and I actually noticed in the list of participants here that some of the developers of the other linear library projects are here. So, and I'm going to come to that in a second. So what RLST does, it has basic, dense, and sparse data types. The dense type use an expression template-like mechanism, like similar to Eigen in C++, to avoid allocation of multi-wheel run, to avoid allocation of temporaries and things like this. So I'm going to explain this. We have started to provide interfaces to LAPACK routines. We do have single node and MPI distributed sparse matrix types. Umflag interface in development. Just very late last night, I actually managed to call the first Umflag routine. And we try to do it with very generic design features. So we are very much interested in designing linear algebra very independently on the specific underlying types. Everything done purely through traits, so that, for example, we can do linear algebra on arbitrary function objects, arbitrary function spaces. So I'm going to come to that as well. So yeah, but first, shout out to existing Rust linear algebra. So I mentioned at the beginning the scientific computing ecosystem, which is taking very nice shape in Rust, and two very important components of this are ND array and algebra. So two existing linear algebra packages which are very powerful. So ND array is really a focus on powerful multidimensional base types. So it's kind of bit modeled on the NumPy ND array type, and it supports arbitrary dimensional arrays, very, very powerful, sophisticated slicing and parallel iterators over these slides. So it's very interesting and fascinating to work with this in terms of complex multidimensional data. It has some LAPACK wrapper source available. Then there's also NAlgebra, which is a very general purpose linear algebra library. It's very strong in terms of fixed matrix support, lots and lots of routines for computational geometry, fixed matrices, but it also has extremely good support for runtime dynamically sized matrices. Recently, developers started working on sparse matrix support, and it has some LAPACK support. It also has some core routines, core decompositions also implemented independently of LAPACK. So where we started actually was first as an experiment to actually, it was for me an experiment X. Can we do something like C++ Eigen with expression templates? And this grew into something larger, namely interest in PD discretization. And where we see RLST using this, we'd like to have comprehensive linear algebra support for PD discretizations and arbitrary objects in linear function spaces. So everything that you need to support PDs. That's kind of our vision. And we see us very much as complementary to these very established packages in that regard. So how does RST look like? We have a number of subtraits. We've got a common trait with some base traits and so on. We've got a sparse module. We've got an operator module with generic operator concepts. We've got dense with dense metric structures, algorithms with advanced linear algebra routines, LAPACK interface, so on. And we've got IO, import, export of routines, matrix, market export, all these kind of things. How does it look like? For example, basic dense matrix data type is defined in the following way. We've got a struct matrix, which has a number of generic parameter. It takes an item, which is a scalar type, like for example, F64 for standard double precision. It has mud-impl parameter with the actual implementation. That's for expression templates. In the next slide, I'm going to explain this. And then we've got a row size and column size identifier, which can either be a fixed size. At the moment, we support fixed size of 1, 2, or 3-dimensional, or it can be a dynamic runtime allocated size where it's a keyword dynamic. And then the only member the struct has is this mud-impl parameter. That's the implementation. The rest you see here, this weird thing, phantom data. So that's our specialty. If you want to have template parameters on the struct that actually not represented in terms of members of the struct. The only real member of the struct is the mud-impl. You create something which is a phantom data, which creates an artificial dependency onto the template type and actually compiles down to a zero size type. So it's just something for the compiler. It's not something you would see in release mode. And then you see this where clause there, and this is where we specify the traits. Item implements a scalar trait, which is comes from an external package, which has lots and lots of routines for numeric data types. RST has these size identifier traits from us, and the mud-impl is a matrix implementation trait. So what's the matrix implementation trait? What's this mud-impl thing? So we've got mud-impl can be done through several things. It can be a base matrix, which is some kind of thing that actually holds data, holds real data. Or it can do an addition, which is just a structure that holds, for the addition, it holds the two matrices or two vectors. So it doesn't store the result of the addition, it just stores left matrix and right matrix in addition. Same with subtraction or scalar multiplication. So it stores the scalar parameter and the matrix. So, and now, whenever we now want to do an operation, let's say, for example, I want to compute 2 times 2.0 times mod1 plus mod2. What is going to happen now that if you look at this, and I'm going to explain this recursive compile time parameter later. So Rust sees 2.0 times mod1. So this is actually a scalar multiplication. So it takes mod1, takes 2.0, and puts them into the scalar multi data type. And then it sees plus mod2. So it sees the addition. So it puts the stuff, the result of this, or the scalar multi object, as one part of the addition operation, and the second part is mod2. And at the end, we've got lazy evaluation. If we want to evaluate this, the whole thing, you use the eval parameter, and then it does a single pass for the data to evaluate this component-wise. And the way the evaluation works is each mod implementation has a get routine, and the get, for example, for addition says, get the element from matrix 1, get the element from matrix 2, and add them up together. And then this way, you get the single pass, and then you get the nice recursive implementation of these operations without having to do multiple passes or do any kind of allocation, like Eigen does in C++. And the types are recursively expanded in compile time. So here the mud-impl parameter, you see a mud F64, and then the first mud-impl parameter is then an addition of the 2.0 times mod1 and mod2. And then if you look into the addition, the left one of this is a scalar mult and so on and so on. So you have this recursive compile time expansion. It's kind of nice. It works very nicely. Sparse matrix support is there. We've done the series sparse matrices, CSR matrices, obviously very easy. We've also done distributed sparse matrices. And for distributed sparse matrices, use MPI. So rows are distributed across nodes, and we have a ghost communicator that's created on instantiation, which is using neighborhood collective operations. So all of this stuff we can do very, very nicely and easily, and it works very nicely. I'm going to jump over the code demonstration right now. I was thinking about showing in detail the MPI demo, but we don't only have another 10 minutes or so left. So if you have time at the end, somebody is interested, I will do it. But right now, I just want to go on. And basically, what have shown the demonstration of how to allocate this MPI distributed sparse matrix and work with this, but it's very straightforward, not dissimilar to other languages. How do we interface LAPACK? So there are very, very good BLAS and LAPACK crates for Rust, which already do the low-level work of interfacing the C routines. We just need to interface it in our code, and that's very straightforward. We have here, I'm not going to go into details, but you can, for example, call mat.linalg.lu.unwrap to do an LU decomposition. You can get the get L, get U, get permutation, you can multiply the matrices as you want, so it works. And the way LAPACK access works is quite straightforward because low-level wrappers are available. And we actually use macros. And on the right pictures, you actually, first example of code from a Rust macro, there's funny $LAPACK_getRF. That's actually a macro parameter where we feed in the name of the actual LAPACK function, depending on the data type that we have, working with single precision, double precision, complex single, complex double precision. You take the corresponding LAPACK function and feed it into the macro so that we don't have lots and lots of code duplication. We just have 4 little macro calls for each data type, scalar data type, and the corresponding LAPACK function. And the rest is done via macro resolution. So yeah, as an example here for something more complex, and also to see how then the corresponding trait works. I'm not going to go too much detail, but I just want to show this. For example, our norm2 function. Norm2, as you see in the upper right picture, is a trait, and the trait just says, hey, you can call norm2 in an object and get a result object trait. And so how does this work? I'm not going to go into all of the details, but just want to show how is this trait implemented. So for dense matrices, it's implemented in the following way. We've got a so-called dense matrix lin-alg beta structure, which actually takes a dense matrix, and so that's when you call the .lin-alg, then it actually transforms this into the dense matrix lin-alg beta structure. It essentially just tests whether the format of the matrix is suitable for these for the underlying algorithms that you have, like with LAPACK and so on. And then we want to implement the norm2 for that. And for norm2, if you have a vector, you can just do the square sum of the elements, take the square root. If you have a matrix, you want to compute the largest singular value. So norm2 only makes sense to implement for objects, for dense matrix objects, where actually an SVD exists. And there you have a where clause where self, so the dense matrix builder, actually also implements an SVD. This is a self::SVD. So this means a self data type, which is dense matrix builder, also needs to implement the SVD. And the norm2 is implemented for anything that satisfies this additional condition. And the matrices, because we also want to support vector, we have also, they need to support also a square sum here, which is just squaring up over, squaring and summing over vector elements. And then we just test for the shape is, first of all, if the shape is 0, we just get if there's a 0 in the shape, we just return an error. If there's a 1 in the shape, we know we have a vector, we just do the usual square sum and square root. And otherwise, we call our SVD routine, and Rust knows that there's an SVD routine available because we have declared that we only want to implement the stuff for anything that has an SVD routine available. And that's kind of the way you do generic programming in Rust. Abstract function spaces. Now, that's something that is very early development. We have lots and lots of discussion around this at the moment, how to do this nicely. We want to do support abstract linear algebra in a way that is opaque on whether you have actual matrices and vectors underlying, or whether I have, for example, orthogonal functions and an orthogonal function in a space of functions. So, and here we experimenting currently with a bunch of base traits. I'm just explaining the one right now that you see here, the pub trait linear space. What is the linear space? It has a field type f, which is a scalar. And then what can the function space do? Well, it can actually produce elements of the function space. So, and there you see something funny here. You see type E, and then you see the lifetime parameter B, and you see element space itself, where self::B, depend on lifetime of B. What does this mean? This means that there's an element type associated with this linear space that actually has the lifetime restrictions that these elements that we have there, their lifetime is not allowed to outlive the lifetime of the function space. Or as it's written here, the lifetime self must be at least as long as the lifetime p. So, and the lifetime of self is the lifetime of the linear space. And this creates very, very nicely expresses a temporal dependency that the object in the function space that you're creating must not live longer than the function space itself. In C++, you would do it in runtime. You would, for example, probably add a shared pointer to your element to make sure that the linear space object would stay alive by a shared reference to that, so it would not be deallocated, something like that. Here you can directly express this as compile time simply with these where clauses applied to the lifetime. So this is a very, very beautiful concept, and then you can create elements. And then derived from this, we've got very specialized spaces, like, for example, if you have a norm space, and the function space also has a norm method which works on elements, or you can have an inner product space, and you can have inner products which work on the elements. And when you have inner products norms, you can do stuff like Arnoldi and so on. So it's very nice. It's very beautiful. We're currently working on this. Yeah, a few last words about the Rust scientific computing landscape. So there's actually a lot of very, very mature stuff already out there. So in terms of basic infrastructure, the packages I'm constantly using are num and Cauchy, which kind of have very, very many useful traits to work with numerical types. By the way, I want to say that the standard lib in Rust is very, very small. So a lot of things that in other languages you as a part of the standard lib, you actually have in Rust in terms of external packages. And the philosophy of Rust standard lib for the Rust core developers is they actually see what the community is doing over many years. And if something becomes very, very established and used by everyone, then they think about including this in the standard library. Like, for example, the way errors are handled with result types. This is something that grew out of external libraries who were experimenting with different ways of expressing errors in Rust. And then when a good solution was found, it was integrated into the standard library. And this is the reason why things like basic traits for numerical data types, they're part of external packages. So here in num and Cauchy. So that's very normal in Rust. Parallel computing for multi-threading, Rayon provides excellent support for fork join tasking, loop parallelism. Then there's RS MPI for high-level Rust MPI bindings, very, very mature MPI bindings, very nice to use. In terms of linear algebra, I already mentioned ND array and algebra, really, really good packages. I'm kind of carefully putting on here RLST, which at some point we hope towards the end of the summer we hope to do our first release. PETC -R is very good wrappers to PETC available. Fair RS, new package by Sarah Exarhazy. She's in France, and this is about creating Rust native linear algebra decomposition, and she's doing amazing work on this. And doing very, very careful benchmarking, comparing to MKL, different LaPeX packages, and she's really showing off speeds that are comparable to these established C++, to these established packages in other languages. So Fair RS is amazing development. And then LaPeX, blast wrappers, and all this kind of stuff is available. Machine learning, very much fast-growing community. Linfa, very, very fascinating, very active project, kind of similar to scikit-learn. TensorFlow has an official Rust bindings, very Rust idiomatic bindings, and PyTorch has, I'm not sure how official the PyTorch bindings are, but it also has very good Rust bindings. And then PD discretizations, I'm mentioning Fenris, very early development, and Swan library in Germany, and BEMPP RS, just own early development project for integral equations. And yeah, so it's growing. It's a very nicely growing ecosystem. Sometimes a little bit Wild West, but Wild West in a good way, because people are happy and interested to try out different things and see with a slightly different language, not which has some new concepts, can we actually create new concepts also for scientific computing? How can we model things with these kind of additional tools, borrow checkings, lifetime parameters, the trade system? So can we do things a bit different there in Rust? So yeah, why Rust for scientific computing? So just to do some more evangelical work here. Mentioned modern language design, many static safety guarantees, error handling, native arsync support. I haven't talked about arsync support. It's very fascinating. C interoperability is really, really good in Rust. Performance comparable to C, C++. Also all uses LLVM. It doesn't suffer from garbage collector. Actually, sometimes, although that's debatable, there are situations where it actually can be slightly faster than C, C++, simply by the strict ownership model that it has. Compilers can better and easier decide when is data changed, when is it not changed. Very much unparalleled tooling, much better than C, C++. Through Cargo, it supports unit testing, benchmarking, document generation. It has plugin support. So one plugins, I showed some LLVM code earlier, that's a plugin. Even MPI execution, there's a Cargo plugin to do MPI run with this. So it works really nicely. And then normal makefile is necessary. We've got these very nice dependency files. Got Rust Analyzer, it's a very good language server, which works very nicely with VS Code, Vim, whatever you want to use. And Rust is not going away. It's got strong investment from Amazon, Google, Microsoft. Somebody here is running the new Windows 11 Insider build. You, I think, already have some Rust code inside. So some Rust code has recently appeared in Windows 11 in the Insider builds. Yeah, to Rust or not to Rust, that's the final question, really, almost the final slide. Rust is a great choice for new projects that do not require CUDA circle. It's a very good modernization pathway for legacy C code due to excellent C interoperability. If you have existing C++ projects you need to work on, extend upon, I don't think Rust is a great choice because interoperability with C++ is difficult. With C it's great, with C++ it's difficult. And also GPU compute, if you depend very much on GPU compute, then Rust is awesome. At this moment, not necessarily the best choice. There's very good OpenCL support because OpenCL, you can just access it through C functions. That's easy. There are some projects working on very early CUDA support, but there's no mature ecosystem yet. So that's a difficulty. For us, it was not such a big problem because ARCHER2 right now is a CPU-based system. And GPU support is quickly maturing. So when the UK at some point buys in GPU exascale system, the ecosystem will be there and will be ready. And if I talk to companies in the area, they do look internally, they do look at Rust. And then training need for RSEs is moderate. Personally, I don't think Rust is necessarily simpler than C++. It's different, but not necessarily simpler, but I have disagreement. Some of my team members say it is simpler, some say it's not simpler. I think it's personal taste, but it avoids a lot of this typical C++ mistakes because undefined behavior in Rust is only possible in two situations, namely, first of all, in unsafe blocks where you disable some guarantees, or it's an actual bug. Safe Rust must not have undefined behavior. If somebody discovers it, it's considered a bug and is being fixed. And so a safety guarantees actually make Rust code much, much easier to maintain than C++. So if you have a new developer starting on a project, then if what they do actually compiles, then you know it's not causing any kind of memory issues, data races or anything. It's in C++ very much you have to work by convention. So, and that's very good. So, and obviously all Rust safety guarantees extend to multi-threaded code. Yeah, so at the very end, just short request if you want to join our community. We've got a scientific computing community which is quite active, rust-sicom.zulipchat.com. And we are also preparing a first scientific computing workshop with Rust, 13-14 July. You can sign up at scientificcomputing.rs. We just, I think yesterday, we put the web page online a couple of days ago. Thanks a lot.
Thank you very much. Do we have any questions from the chat? I think as we were going, there was one from Julian Lenz. Are you targeting interfacing with other libraries in your own work? I think you discussed how Rust can interface with things like RBAC, but
Yes, a couple of things. For example, I briefly mentioned that we are doing Unsafe interface first at the moment because we don't have resources right now to build our own sparse direct solver, and later we also interface mums. So where it's useful, we interface other library, but we at some point, my vision is that at some point there's a very much Rust native ecosystem. You can use full power of Rust, but obviously it takes time. And there are excellent libraries from other languages. I have no problems using them.
Okay, we have another question from Stan. Do you have any idea whether the MPI interface leads to an increased latency compared to native cores, e.g. C++? For Python, you get big overheads from non-NumPy database data types.
I would not think so, because I don't see it, because in Python things have to go through the interpreter, and it's the interpreter which is making everything slow. Here, everything goes through LLVM. It's just one, at the end, it's just one thing from LLVM generator, it calls another, calls into a C library. So there should not be any overhead, but obviously I haven't measured it. Oh, well, not obviously, we haven't measured it, but I don't think it would, I don't think it will happen.
Okay, and Mark asks, do the safety guarantees have any impact on multi-threaded performance?
No, because these are compile time safety guarantees. So it's nothing that is checked at runtime. Everything is checked at compile time. You have to, in certain cases, sometimes you need runtime safety checking. Sometimes it's not possible to do everything in compile time. Like in shared reference C++, sometimes you need multiple threads having a shared reference to something, and then sometimes you need to do runtime checking of these safety guarantees. And there are equivalents to these shared pointers in C++. For example, these reference counter types exist in Rust. If you have a situation where you need to use a reference counter type, then obviously that's a similar performance hit like when you do a reference counter type in Rust. Like it's the same performance hit you would have in C++, but in a lot of situations you don't need it. And obviously, when you do need it, it's a conscious decision about using this.
Okay, I think that's all the questions we have from the chat, as far as I can tell. I'd just like to take the opportunity to thank you again for giving a lovely talk, and thank you everyone for joining. We had quite a large attendance this week, which was excellent. So I hope to see you again in future ARCHER2 webinars.